Let's talk about trig substitution. In this video, I'm going to do the problem you see on the screen here. We're going to integrate x cubed over the square root of x squared plus 16. All right, so I see the square root of x squared plus 16 in my denominator. The addition between x squared and 16 tells me I should do a tangent substitution because tangent squared plus 1 is an identity. So I'm going to sub in x equals 4 tangent of theta. I'm choosing 4 because that's the square root of 16. The idea is once this gets squared in the x spot, I'll also have a 16 here and I can pull it both. All right, so we have theta in the right half of the unit circle minus pi over 2 to positive pi over 2. That always comes with the tangent substitution. And then I'm going to compute the derivative of 4 tan theta is 4 secant squared theta d theta. No need to divide by 4 or anything. I can just plug this straight in for the dx right there. All right, so all together, this becomes 4 tan theta cubed. That x cubed in the numerator is just sort of along for the ride. It wasn't the reason we chose the trig substitution, but everywhere there's an x here, I've got to put in 4 tan theta. So x cubed becomes 4 tan theta cubed. And then in the denominator, square root of 4 tan theta squared plus 16. And then, of course, the dx is all of this 4 secant squared theta d theta. All right, so I'm going to very carefully start to expand and simplify in this integrand here. So in the numerator, I have 4 tan cubed. 4 cubed is going to be 64. So I have 64 tangent to the third power. In my denominator, 4 tan squared is 16 tan squared. Everything else stays the same. Okay. Now, in this denominator, we have kind of our typical expected trig substitution business, right? So both of these terms have a 16. So I'm going to factor that 16 out, and it can actually get its own square root. So what's left in here is tan squared plus 1. One thing I'll do here to kind of keep things tidy as I go, this root 16 is 4. It's going to cancel with this 4 over here, so I never have to multiply them into that 64. This will cancel here. All right. I'm also going to take this square root tan squared plus 1 and put in my identity, right? So we put tangent in here so that this identity could come in. Tan squared plus 1 is secant squared. And of course, the square root of something squared is its absolute value. And because theta is restricted to just the right half of the unit circle for this tangent substitution, all the cosines are positive, which means all the secants are positive. So I'll say, okay, I'm going to replace this with regular secant because of this limitation on theta. Right, so then this denominator, this whole thing that I've circled in red, boils down to secant. All right, so I have 64 tan cubed on top. This 16 in the root has canceled with the 4, so it's just secant theta down here. And then we have secant squared theta d theta still on the end with that 4 canceled. There's still a little bit more cancellation I can do. So this secant on the bottom cancels with one of these up here. So I have altogether 64 tan cubed secant theta d theta. Okay, so from here, we don't have a straightforward antiderivative rule for tan cubed secant, but this is a problem type that we learned in a previous section. This is a combo of tangent and secant. So I can either pull out a secant squared to sub in for tangent. I don't have enough secants to do that, so the other way is the way. The other option is to pull out a tangent secant and sub in for secant. So that's what I'll do. So I'll take one of those tangents, the only secant down here. So this I'm saving at the end because that'll be the du for u equals secant theta, which means that the rest of this needs to be in terms of secant. I don't have any plain secants left over, and then this tangent squared I can write as secant squared minus 1, which will be u squared minus 1. So altogether, 64 is still there. And then I have u squared minus 1, that's the tan squared, and then the whole rest of it is du. I can distribute the 64, or I can just carry it down into my answer. Either way should be fine. Why don't we leave it on the outside for this one? U squared and minus 1 are going to be reverse power rule. And then I'm going to take these u's and replace them with secant theta. So we've switched back into theta and we've done the integral step. But if we go all the way back to the beginning of the problem, it started as x's. So we need to give our final answer in terms of x's as well. Now, what we have here is all in terms of secant theta. Because the original substitution was tangent and I need a different trig function, I'm going to bust out my SOHCAHTOA triangle. This one, because it's tangent to secant, you could also use a trig identity to connect the two, but I'll do SOHCAHTOA because it works every time, no matter which trig function you need. Right, so to replace secant theta with a function of x, I'm going to take the original substitution, x equals 4 tan theta, and set up a SOHCAHTOA triangle. All right, so if I divide 4 on both sides, I get that tangent theta is x over 4. So this means, like, in my answer, if I had a tan theta to replace, I could put x over 4. Or if I had just a plain theta, I could say arctan of x over 4. But since we need a different trig function, we're going to interpret this as the TOA of a SOHCAHTOA. And then we'll start up a triangle. This is adjacent, opposite, and hypotenuse sides. I'll use x as the O side, 4 as the A side. And then anytime I have two sides of a right triangle, I can use the Pythagorean theorem to solve for the missing side. So here I have 4 squared plus x squared equals h squared. So square root of 16 plus x squared is that hypotenuse. Fill that in. And then this is also the moment that we notice square root 16 plus x squared. They've swapped positions for no real reason, but this is a piece of the original integrand coming back into our final answer, which kind of makes sense and is comforting that we're on the right track. Once all 3 sides of this triangle are filled in, we can get any trig function we need using SOHCAHTOA. So again, in our answer, we're replacing secant cubed, or sorry, just regular secant. So I need secant from here. Secant is 1 over cosine. So this is 1 over the ka from SOHCAHTOA. That's going to be h over a. So that is the hypotenuse side, root 16 plus x squared, over the adjacent side, which is 4. So in both of the spots in my answer where I have a secant, I'm going to put this expression. All right, so we come back to the bottom here. 1/3 all that stuff cubed. So root 16 plus x squared over 4 cubed. And then minus just regular secant, root 16 plus x squared over 4. And that is my final answer.